Probability histograms allow us to find area under curves and have that actually as a percentage or a probability. We'll look at this through example using some data. We took the weights of everyone in the class and then we divided it into equal classes. So I'll put the data we received. So notice in our class intervals we end on 44 and then start on 45. That's so if someone weighs 45 kilos, we know which column to put them in, which row to put them in. If we had 45 and 45, we'd be in trouble. We wouldn't know, if we started at 45 and ended at 45, we wouldn't know which one to put them in. Okay, so this is the data that we had. From here, we'll calculate the relative frequencies. So relative frequency is frequency of this guy occurring divided by the total number of trials. And we're just leaving these as decimals for now. So I'll do that all the way down the column. And hopefully we'll get 1 when we add these together. Okay, end up with 1 there. Okay, so your temptation would be just to straight away draw weight and relative frequency and start making your histogram. Okay, 2 things we need to be careful about. Okay, the first one is in our weight, we're not going to go 35 to 44 and then 45 to 54 and draw bars like this, because histograms don't have gaps in between them. So what we need to consider is what the real true class is. So this first class here really goes up to 44.5. And this, so gets that section here. And this second guy really goes back to 44.5 as well. So the true class intervals is always 0.5 outside of what your class is. So for the first one, it would be 34.5 to 44.5. Okay, and you continue that same idea all the way down your classes. This should make sense, because if I had someone come in that weighs 44.1 kilos, and I'm looking at these limits, I would round this to 44 and it would go in the 35 to 44. Okay, same with everything up to 44.499999. That would still go there, which makes sense why our true class limits are as they are. Okay, so that's one thing that we're aware of. The other thing that we need to be really careful about is the heights of these bars. So it's not just the relative frequency. This sentence, the height is found by dividing the relative frequency by the width of each column. So the width of these columns, if you imagine it on the histogram, it spans 10 kilos. So my width is 10, which means I'm going to divide all these relative frequencies by the width, which is 10. So 0.077, 0077 rather, okay, and follow that all the way down. So if you chose these initial classes to be maybe 35 to 64 and then 65 onwards, 65 and 90 for example, you'd end up with a width of probably 30 and you'd be dividing here by 30 instead of dividing by 10. Okay, so that's the whole idea. Okay, so from here we can finally construct our probability histogram, and we'll be graphing the true class limits with the column height. Okay, these two are the ones that we'll graph. It is a little bit tricky to think of how you're going to label these axes, especially the vertical one. I'd look at my column heights and see that the biggest one is 0.0308. So I'm going to go from 0 to probably 0.035, and I'm going to break that up into sections of 5. So I go from 0, 0.005, 0.010, etc. Okay, so there's our probability histogram. Probabilities on the vertical axis, weights down here, and this thing is just showing that I've broken the scale. So I need to do that, otherwise I would have had to have a big gap where it goes like 4.5, 14.5, 24.5. There'd be a gap before I start having those. So I wanted to get rid of this section in the middle. I achieved that using that little sign. Hopefully you've seen it before. Alright, so the whole point of doing this was so we could answer some questions. So find the probability of a student weighing between 65 and 75 kilograms. To do this, I'll look on my graph and I'll find the area between 65 and 75 kilos, the area under this histogram. So I want to find this shaded area, which I'll call area 1, and this dotted area, which I'll call area 2. And then add them together. So the first rectangle, need to think of its dimensions. So from 65 to 74.5 is 9.5, and its height is 0.0231. Rectangle 2 is from 74.5 to 75, so it's a pretty narrow rectangle, only 0.5 wide, and it's 0.154 high. So if I want to find the probability of someone weighing between those weights, I just need to find the area of those two rectangles. So the area of rectangle 1, 9.5 times 0.0231. Area of rectangle 2, 0.5 times 0.154. Correction, 0.0154. I'll get a probability of 0.227. So about 23% of my population weighs between those two weights. Okay, let's have a look at the next example. If a year level consists of 200 students, how many would you expect to weigh over 90 kilos? So I'll first need to find the probability that a student weighs over 90 kilos. I'll find where 90 is, so roughly here, and find the area of all the things to the right of that point. So I'm really just finding the area of that shaded section. I'll draw it here. Its dimensions are a width of 10 and a height of 0.0077. All I need to do to find the probability is find the area of that rectangle. Okay, but I'm asked for an expected frequency. So I'll cast my mind back to lesson 1, lesson 2. Expected frequency is the relative frequency, or the probability, times the number of trials. So I know there's a 0.077 chance of getting someone over 90 kilos. I'm essentially picking 200 students and weighing them, seeing how much they weigh. I'll expect 15.4 of those students to weigh over 90 kilos. Okay, so just looking back on this, there's a fair bit in that table. Key parts are finding your true column width, okay, and then dividing the relative frequency by that column width, so that when we draw the table, when we draw the histogram, we can use areas for probabilities. If you don't do this division, then you're going to get crazy answers when you try and calculate probabilities. Alright, have a go at those questions at the bottom. Good luck.